Really?
She said she always, she never got picked as a kid, so she hates it.
Oh, that's sad. Of course, I never got picked as a kid either, so. Dr. Roth would play, though. So you'd play Heads Up 7-Up with him, wouldn't you?
You want to play right now?
Right now?
Yeah.
Sure. I have no idea what that is.
Heads Up 7-Up? You never played that?
Now we gotta teach Dr. Rock what it is. Like,
Yeah.
we can't.
You can explain it to him.
Okay, we'll get Julia
Do
to
a demonstration round.
Okay.
Yeah.
Oh, for heaven's sake.
We're gonna explain it.
So what class am I delaying here?
Stats.
Okay.
This has absolutely nothing to do with stats, by the way.
Oh, really?
Yeah.
You could make
There-
a stats problem.
I could make a stats problem out of it.
We're showing him how to play Heads Up
Dr.
7-Up.
Rock is how to play.
Dr. Roth doesn't know what Heads Up 7-Up is, so.
I texted you.
Wait, you got.
I know. It's fine. Yeah. Huh? Was
Probably.
it? No.
Be injured?
No, you're not going to get injured. Well,
Excuse me.
Depends. If you trip or something.
Okay, everyone put your heads down. Good, now you're just gonna touch someone's thumb. Just one person.
Oh, just one person?
Yeah.
Okay.
But don't let them know.
Yeah, you were like talking, so like they.
Oh, so
That's what they're
okay,
gonna
we'll
guess.
start
Yeah.
over.
Okay. Okay, heads
Okay.
up. And then everyone who has their thumb down is gonna stand up and guess who put their thumb down.
Wow. Alright, I'll start. Julia.
Yeah.
So then they'd switch.
then they would
Then
swap.
yeah, then Susie
Oh,
would
okay.
come up. Yeah.
Okay.
Then Levi.
Dang it.
Dr.
So then you.
Yeah.
Yeah, so then we'd all sit down and they'd all come up.
And
then
and you would
play.
repeat. Yeah.
Okay.
Yeah.
Well, that's bizarre. How did those two know?
I don't know.
They
How did
Your
your
hand
hands?
was kind of soft, so I was like, I was gonna guess Levi, because it was like a.
So you might get injured.
Yeah, that's what Heads Up 7-Up
Oh,
is.
thank you. That was great fun.
Yeah.
Thanks for playing.
Sure.
It's a stall tactic.
I see that.
Yeah.
Okay.
That's what that is. But now you know what it is.
Now I know what it is.
Yeah.
That's good. I learned something today. I'll put it in my annual report.
There you go.
Now we gotta teach Ryan.
No, Ryan already knows how to fly.
Abstract.
I know.
Ryan, all right. Whatever.
I had fun.
When she hits your thumb, she'll walk away laughing.
It's hilarious. All right, what were we doing? I forgot. What's that? Oh, that is recording.
That's the best part of rewatching your lectures.
Oh, it's just the random stuff that happens in class.
Oh yeah, I like watching it on like half speed. That's really funny. Because on YouTube you can control the playback speed,
Yeah.
and everything's just like all slurred, and it's hilarious.
That's funny. I didn't know that. I didn't know that you could watch it back at half speed on YouTube. That's weird.
You could watch it back at double speed too, but that's too fast.
I can barely keep up now.
Yeah.
All right. Let's talk about some of this material. Now, we talked last time about starting to do hypothesis testing, what the null hypothesis is, what the alternative hypothesis is, what it means to make a type 1 error, what it means to make a type 2 error. We're going into forming hypothesis tests for specific types of distributions with, say, how the test about a proportion works, or mean, or difference of means. The concepts are all the same. So to illustrate some of the more important concepts that go along with it, as far as what's the type 1 error, how do you calculate that probability, what's type 2 error, what's significant, the p-value for a test is, and those kinds of things. Let's do some specific examples. So I want to look at 28.3 in the handout that I gave you. All right, so in 28.3, you're given a density function, f of x is equal to theta plus 1, x to the theta, assuming that, X is between 0 and 1. In this one, they're giving you actually two simple hypotheses. Remember, simple hypotheses are the ones that purport that the parameter is actually equal to a specific value. So basically, this one's telling you you have two possibilities. You have the possibility that theta could be 1. That's the null hypothesis. This one uses an H1. I think your book uses an HA. If you see H1 versus HA, they mean the same thing. It just means the alternative hypothesis. Those are your two hypotheses that are possible. We're going to reject the null if we take a single value from the distribution and that single value actually turns out to be bigger than 0.9. All right. So let's think about this from a picture standpoint, if you will. So our graph of our function would look something like, oh, hey, maybe something like that. Something like this, depending on what the theta is, 1 or 2. If theta is 1, of course, it would just be a line, right? Because it would be x to the first. But in general, x to the theta would look some sort of a curve. All right. And then, so this goes from 0 to 1. Our critical, typically whatever value separates the region that you're going to reject in versus the one that's not is called your critical value. So in this case, our critical value would be the 0.9. And we're going to reject if we land in this region. Okay? So this is the rejection region or the critical region. If I could spell the word critical, that would be helpful. Both of those words mean the same thing, rejection region, critical region. I believe your book says critical region. Doesn't matter. It's the region that if whatever your sample statistic is, in this case, we're taking a single value and seeing if it's 0.9 or bigger. The critical region, the rejection region is whatever your sample statistic is, if it lands in that region, you're going to reject the null hypothesis. Okay? That's what it means. All right? So in this case, we're looking for x's that are in this region. Okay, so now remember, a type 1 error is you rejected the null hypothesis when you shouldn't have. Okay? So the null hypothesis is true, but the sample statistic that you came up with indicated the null hypothesis wasn't true, or at least was very unlikely. Okay? So in this problem, it's asking us to calculate the probability of a type 1 error. Remember, that was the alpha. We talked about alpha last time. Now, in most of your statistics that we're going to do, the alpha, I mean, literally the alpha is the significance level. It's the probability of making that type 1 error. Usually that's what's given to you. In this case, we're actually trying to calculate it, given the region. Usually it's the other way around. I want the probability of making a type 1 error 0.1 or 0.05 or 0.01. We've done that kind of stuff with the confidence interval stuff in the last chapter, right? So the alpha is something that you're typically given, and then you go figure out what the rejection region is from it. This problem is given to you in reverse. It gives you the rejection region, and it wants you to find the alpha, the probability of making that type 1 error. Okay? So that's what the alpha stands for. So in this case, again, probability of the type 1 error is we want to calculate the probability that the x is greater than 0.9. That is, I rejected the null hypothesis. The statistic that I found landed in the rejection region, given the null hypothesis is true, given the theta is 1. That's what we're trying to calculate here. This is the alpha. So if theta is equal to 1, our PDF is just simply 2x, right? We agree with that? Okay. So if I want to calculate this probability now, how are we going to calculate it? Silently, apparently. You could listen to that on double speed, it wouldn't matter. What were the x values that the PDF's defined over? 0 to 1, right? I want to know the probability is greater than 0.9, so how are we going to set it up? Integrate from the 0.9 to 1? Yeah, the 0.9 to 1? So we just get x squared when we integrate. So we'll get 1 minus 0.81. We agree with that? So we get 0.19, so we should have the answer C in that one. All right. So that's, again, this is just, we're given the region, we wanted to figure out what the probability of making a type 1 error is. So in this case, you're going to reject about 20% of the time when you shouldn't. It's probably not a very good significance level. Okay. But that's, I just want to illustrate the point. We can do the other way around too. Remember we also talked about type 2 errors. Type 2 error is the probability that you don't reject when you should. Right? So if I want the probability of a type 2 error, we use, beta for that one. Again, if we think about the picture in this case, we want, here's the PDF. Then in this case, it really would look like that because in this case, if the null hypothesis should be rejected, the theta was 2. So we really should have something that looks like a quadratic, right? Our rejection region would have been in this region over, the rejection region's in terms of the original one, but your rejection region's over here for if the null hypothesis is true or false. But this one would be your region that we're interested in for the beta, right? That you didn't reject when you should have, right? Now, they didn't ask for this one, but we want, for beta, in this case, we want the probability that x is less than 0.9 given that theta was actually equal to 2. Right? Didn't reject, right? This is not reject. And I could have put equal to. Again, we have a continuous distribution, so the equal to wouldn't matter, right? But this is do not reject, and we should have. Right? That's a type 2 error. Okay. So in this case, what would we set up? Okay, so the theta is 2, so the f of x is, say it again. Okay, good. Okay. Good. And then 0.9 cubed is what, 0.729? Being a, I'll say mathematically inclined kid instead of something a little derogatory. memorizing different things like powers of 2 and powers of 3 and square roots of numbers pays off in a situation where you just write down 0.729. All right. That's a pretty high probability of making a type 2 error. Right?
There's no one minus.
The 1 minus is going to be the other thing that we're going to talk about. So, yeah. So this is literally just the probability of making a type 2 error. That's a high probability of making a type 2 error. In fact, when we talk about the idea of power, which is what you were referring to, the power of this test, it's 1 minus the beta, 1 minus the probability of making a type 2 error is 0.271. Obviously, more powerful tests are ones that you want to get that closer to 1. Thinking about what the power here is trying to measure, remember, you want to make sure that what you're really trying to do is making sure that you don't reject when you shouldn't reject and do reject when you should reject, right? What the power here is measuring is you've made a change, maybe you've made some sort of a manufacturing change. The manufacturing change actually did make a difference. You're just not seeing it in the sample that you took. In which case, you might be throwing out a good thing that happened because you didn't get the result you thought you wanted. So from the power of a test, the power says, okay, I'm pretty certain that when I'm rejecting, I'm confident that I should be rejecting. Right? And then the other way around, if I'm not rejecting, then I'm confident that I shouldn't have rejected. Right. So those are the difference between the alphas and the betas. All right. The power, again, is the harder thing to get a handle on. Right? Calculating the probability of, especially when you've got compound alternative hypotheses, right? If I want to know that something actually has changed, the change might have been small or the change might have been large, but you don't know to start with, right? So knowing exactly what the power of the test is on a compound hypothesis is hard. If you would have said that the null hypothesis was theta equal to 1 and the alternative hypothesis of theta is greater than 1, then notice my power of my test would have depended on the theta, because I would have been able just to replace it with a 2, right? And then the beta depends on what the theta was, which is a hard thing to try to control. And like I said, we're going to talk about that later in the semester of how you can try to figure out what they refer to as the most powerful critical regions. Usually, the way you handle power is just by taking bigger sample sizes. Right? In this case, the problem is that you've got a sample of 1. But of course, we're also just trying to illustrate concepts, and it's a lot easier to illustrate the concepts when you're doing smaller samples and smaller things. All right. That okay? Yeah, Haley.
Can you go over it one more time? How you know which hypothesis to use when you're doing like the probability of the errors?
Okay, so type 1 error means that you did reject the null, but you shouldn't have. Okay, so the null hypothesis was true. So that was why we used the theta equals 1, because that was the null hypothesis one. Okay. The beta, the type 2 error, is you didn't reject and you should have.
Okay.
So that was why we used the theta is equal to 2 in that one. So basically, type 1 error is null hypothesis is true. Type 2 error is alternative hypothesis is true.
Okay.
So in that case, numbering the hypotheses maybe 1 and 2 would have been better, but because then it would have been, you could have kept them straight that way. But that's not what they've done. All right, cool. Any other questions before we do the next problem in the packet here? The 28.4? Now, one of the reasons why I want to do 28.4, besides going over critical regions, again, from a different concept, I just want to remember some properties of the Poisson distribution, too. All right. So, in this case, you're going to test the null hypothesis of the theta being 5 versus the alternative hypothesis of it not being 5 using the sample mean. Of course, in this case, the sample mean is just 2 pieces. So what's the probability of the type 1 error if you've already got a predefined critical region? So this absolute value of the mean minus 5 being greater than or equal to 4. How can I convert that to a statement that doesn't involve absolute value? Let's start there. Say it again.
Like -4.
Okay, so you could do the x minus 5, or x bar minus 5 needs to be less than or equal to -4, right? Or the x bar minus 5 is greater than or equal to 4. If it were less than or equal to, we would have pinched it in between, right? Which we're actually going to do here in a second anyway. So this says that our x bar needs to be less than or equal to 1, or x bar is greater than or equal to 9. Just rearranging it. Would you agree with that? Okay. This is where I said that I wanted to do this particular type of problem because I want to be reminded of stuff with Poisson distribution. So the mean, of course, is defined as the sum of the two divided by 2. But what do we know about the sums of Poisson random variables? If you do a sum of 2 Poissons, what kind of random variable do you get? It's still a Poisson, right? What do you do with the means in that case? If you have x, if x1 has mean lambda 1 and x2 has mean lambda 2, that's add them, right? Yeah, exactly. So sums of independent Poissons are still Poisson, and I can just find the mean by adding the means, right? So if we convert this into a statement about the sum of the random variables, this would be x1 plus x2 over 2. I don't know why I put parentheses around that when I wrote it as a fraction. I could write it that way, right? And then write it as x1 plus x2 is less than or equal to 2, or x1 plus x2 is greater than or equal to 18. I went through all of that because now I can talk about probabilities of the random variable that is just a Poisson random variable, right? Because now this x1 plus x2 is a Poisson, this x1 plus x2 is the same Poisson, and I know something about the mean now, right? Because remember, we're trying to do probability of a type 1 error in this case. Type 1 error is that you assume the null hypothesis is true, but you reject it anyway, right? So we want the probability that this is true, given the theta was actually equal to 5, right? Well, if the theta is 5, what's the mean for the sum of x1 and x2 then? If the theta is 5, so the theta is representing the mean for the Poisson distribution, what's going to be the mean for your x1 plus x2 then? It's 10. Yeah, we just add them together. Good. Okay. So in this case, we're assuming that we've got a random variable, Poisson random variable, with mean 10. And I want to know the probability that that random variable is less than or equal to 2 or greater than or equal to 18. So just to write that down, x1 plus x2, I'll call it y, is Poisson with mean. In this case, they tell you it's mean theta, so it would be mean 2 theta, right? Because each of the x's has mean theta, right? We want the probability of a type 1 error, so alpha is our name that we give the probability of type 1 error. That's the probability that y is less than or equal to 2 or y is greater than or equal to 18, given the null hypothesis is true. The null hypothesis in this case is theta is 5, right? We agree with that?
So it's the null is true, so we did reject. Or
We rejected it but shouldn't have. Yeah. So this is a description of our critical region in terms of the y. So we rejected, but we shouldn't have. So that's our type 1 error. Okay. So let's think about how we would compute this. Well, y is Poisson. Well, Poisson's discrete. It has a support from 0 to infinity. In particular, that sum would suck, right? Okay, so probably don't want to do that. So let's do the complement instead. So this would be 1 minus the probability that the y is in between what two values? So I want to get rid of the 2 and get rid of the 18, right? So it'd be 3 and 17, given that theta is 5. Keeping track of where that equal to sign is. All right, so let's think about y again. Y is what kind of variable? Poisson. And since we're assuming theta is 5, its mean is 10, right? So we now know what the PDF for y looks like, right? The PDF for y would be what? Okay, e to the negative 10. Y, yeah. 10 to the y, good. Over y factorial. That would be this PDF, right? If I want the probability that we're between 3 and 17, what do I need to do with this PDF? I got to sum it up, right? I got to do the sum from y equals 3 to 17. And we've got 1 minus still out in front of it. Does that look like one of our option choices? Yeah. So there's our probability of making a type 1 error, which we could compute if we really, really wanted to. I really, really don't. Excel has a cumulative Poisson distribution function built into it, so if you really, really wanted to, you can do it from there. Or calculate them in individual cells and sum up the cells. Do that too on Excel. Everyone okay? All right, let's do another one with power, just so that we understand what's going on with power. So let's look at 28.7. And again, mainly I'm going through these because, again, I want to make sure that we understand what the different definitions are, because once we understand the definitions, the calculations of the test statistics that we're going to do later on back in the book are all just based on the type of distributions we have. So it's going to be the same stuff. You're just going to vary what your test statistic is based on the type of distribution that you're talking about. So right now I'm just trying to concentrate and make sure that we understand the different definitions, because section 7, 1, 2, and 3 and 4 are all essentially all the same. It's just the different, what are you trying to test it for? So anyway, 28.7. Single observation from a uniform distribution. They give us a critical region. All right. So we want power. Power is 1 minus the probability that you take or make a type 2 error, right? So let's do type 2 error first. Type 2 error again means what?
You shouldn't have rejected it, but you did.
That's the other way around. That's type 1. Type 2 is that you didn't reject and you should have. Yeah. You did exactly the opposite. You did type 1. Yeah. So type 1 is you didn't reject, but you should have, right? So in this case, didn't reject is what? So it's the probability that X is less than the C is the probability that you did reject, right? So didn't reject would mean that X is greater than or equal to the C. Yep. The equal to. When we're in a continuous distribution, of course, the equal to doesn't matter. But the previous problem we had Poisson where it would have mattered. So that's the reason why I put it in there. Didn't reject. X is greater than or equal to C given you should have. If we should have, what's the condition that we should have? Theta equals 2. Good. Okay. All right, so let's concentrate on the theta equals 2 part. If theta equals 2, X is a uniform distribution on what interval? What is it? Sorry. 1 to 4? Right? So then this probability would be what?
From 3 to 4.
Okay. No, not 3 to 4. From wouldn't be 3. Because I'm greater than just a C, right?
C is between.
C is between 3 and 4, but we don't know what C is, right? So it'd have to be from C to 4, right?
Oh.
And then what function are we integrating? The uniform one, okay. 1/3, yeah, good. That's the easy one, right? It's just 1 over B minus A.
Oh.
That one's the easy one, isn't it? So this just ends up being what? 4 minus C over 3? Yeah. So that's our beta. So then the power is the 1 minus beta. And we get C minus 1 over 3 when we simplify. Does that make sense? Okay with that? Do you want to do another one with power? Yeah? Okay, let's look at 28.15. See, I had one already picked out. Look at that. It's like I prepare for class or something. Now, some days it doesn't necessarily look like I prepare for class, but I promise you I look at this stuff ahead of time because statistics isn't my area. So I look at this class and numerical a lot.
What did you say? 28.5?
Why 1.5?
1.
Yeah, 28.15, sorry. I meant to say 1.5 if I didn't.
I heard the 5.
Well, if you didn't hear me say something, I probably didn't say it, because I don't think anybody has any problem hearing me say anything. It might be garbled, I might stumble over my words, but usually people don't have a problem hearing what I say.
I'm kind of bad at hearing, so.
Or hearing that I say. Maybe what I say is a different question. Now you can listen to that back at half speed.
Yeah.
All right. So 28.15. We're going to take a single sample from an exponential distribution. They've written it a little bit differently in this case, but that is an exponential distribution. They just have the lambda. The lambda is 1 over theta, right? We're used to seeing it as 1 over theta. Okay. Null hypothesis tested against the alternative hypothesis, and they give us a rejection region of x is greater than or equal to log 10. So again, power is 1 minus beta. Beta is that measure of probability of type 2 error. So let's just do that first. Type 2 error again means what?
HA is true.
Did reject.
Yeah, it didn't reject. Good. Yeah. We'll get there eventually, all right? Yeah, HA is true, but the rejection, the critical region didn't show that. The sample test, the sample statistic didn't show that. We didn't reject. All right. If we didn't reject, what has to be true in this particular case? If we did not reject, what has to be true? Because that's the given part. I agree with you there. But if we did not reject, what had to be true about the x?
Oh, it's less than.
Less than log 10, right? So we have the probability that x is less than log 10 given, wow, that is a funky looking lambda. That our lambda is between 0 and 1. That's not a much better looking lambda, but it was better than the less than sign or whatever the heck I drew earlier. Greater than sign. I would like to blame it on the pen because the other side of the pen was damaged, so I had to flip-flop it and put it back in there to get it to work. I need to get new tips for the pens. All right, anyway. I want to calculate this probability. We're given our f of x, so what is this? How are we going to calculate this probability in this case?
You don't have to double anything?
Well, lambda is a constant no matter what, so it's just we don't know what necessarily that constant is. So we want to calculate the probability. What should we do? Given the PDF that we have. We can play Heads Up 7 Up again. But we're given a PDF. How do we calculate probabilities when we're given PDFs usually? Integrate? Yeah, what do we want to integrate in this case? What's our interval?
0 to log 10.
0 to log 10, good. What's our function? Cool, good. Antiderivative? Do I have the derivative of the exponent sitting out in front, kind of? Yeah, the antiderivative is going to be what? What do I need to adjust? The minus sign, right? So it's just going to be minus e to the minus lambda x. Evaluated from 0 to log 10. Put in 0, we get 1. And we put in log 10, we'll get e to the minus lambda log 10. I flip-flopped it because there was a negative in front, right? I just flipped them around. Now can I simplify that e to the negative log 10 thing? Or negative lambda log 10 thing? Well, if that negative lambda weren't there, what would you say it was? 10. How can I make that negative lambda not be out in front? Yeah, move it up to the exponent, right? Right? So that'll just give me 10 to the negative lambda, so we'll have 1 minus 10 to the negative lambda. And this is where the problem was mean, because that's one of the answers, but this is not the answer. Why is this not the answer?
1 minus.
It's 1 minus that, right? Remember, what's asking in this case, it's not asking for the probability of type 1 error, it's asking for the power. Power is 1 minus beta, which is 10 to the negative lambda. So your answer is A, not E.
You just put, I think, lambda as exponent because you can take the natural log of that and you could bring out.
Right. Yeah, that's one of our log properties, yeah. Is okay? All right. So let's do one more. That gives us ideas with probabilities of type 1 and type 2 errors. Let's look at 28.27. is combining type 1 error and type 2 error. We've got some unknown k in there that's defining our critical region. But they tell you that the probability of making a type 1 error is 3/4. Can we figure out what the probability of making a type 2 error is? Well, if your probability of making a type 1 error is 3/4, I'm not sure what the point of the hypothesis test is, but we'll go with it. Having a 75% of the time you're wrong is not a good percentage. Okay. All right, but we'll go with it. So let's do the if part first. If the probability of type 1 error is 3/4, how can we get an equation to solve using that information? What's type 1 error again?
Do not reject pressure. Null is true, but you rejected.
Null is true, but you rejected. So you rejected, but shouldn't have, right? That's type 1 error.
I can't get this right.
You flip them every time. All right. So the alpha here is the probability that you rejected, but shouldn't have, right? Probability that you rejected. Rejected is x is less than k. That's how they define the critical region in this case, right? Shouldn't have. Shouldn't have is alpha. Oh, they used alpha. Dang it. I'm going to put a hat over this. Haley likes my joke about the hats over the top of variables.
That one I didn't find funny.
What, you didn't find what's funny at all? Yeah, about the pea hat. Yeah, I put a hat on it so it doesn't catch cold when it goes outside. I knew it would irritate her, which is why I said it. I'm only putting a hat over this one because they used alpha in the problem. Null hypothesis is true, says alpha for the problem is equal to 2. Yeah, good. All right. We know that this probability is 3/4, right? They tell us the probability of making this error is 3/4. All right. So how would I calculate the probability that x is less than k? Okay.
From 1 to k.
Okay, good.
2x and
Good. And that has to equal 3/4. Antiderivative for that will be a negative x to the negative 2. So you get 1 minus 1 over k squared is 3/4. So that tells us that k is 2. I know I did that quickly, but I got about a minute. I figure you can always go back and check. Well, listen to it at half the speed. Yeah. All right. So now it wants the probability of type 2 error. Type 2 error means, again, what, Sarah?
Didn't reject but should have.
Didn't reject but should have, right? Didn't reject in this case says, what about x?
Greater than.
Yeah, good. It's greater than k. Technically greater than or equal to k. Given should have. Alpha is 4. Right? But I know what k is now. K is 2. So when we set this up as an integral, what's the integral going to be? Integral from... we can do 1 minus 1 to 2 if you want, right? Because it's bigger than 2, right? So it should be 2 to infinity. Because it just says x is greater than 1's our support. So it'd be 2 to infinity of what function? 4x to the negative 5. So antiderivative for that is negative 1 over x to the 4th. If I plug in infinity, I'm going to get 0. That's technically doing an improper integral and doing a limit. I'll be improper about it. Okay. So I get 1/16. So my probability for making a type 2 error is actually fairly low, but probability of making my type 1 error is pretty high. So anyway, I'll give you an assignment next time. How's that sound? Sounds great?
So
right.
we'll back into.
Probably Wednesday. All right. So next time we'll get back into the book stuff, come up with actual test statistics for familiar distributions like population proportion, population mean, difference of means, and those kinds of things.